The last topic for this week is free body diagrams. Free body diagrams, or FBDs, are used as an aid to construct equations of equilibrium, which we have already discussed in the previous lesson. The construction of FBDs themselves is done according to well-defined steps, which we will cover as we walk through the following example. This example demonstrates a beam with a point load. Suppose we wanted to find the forces acting on the beam below. For the purpose of our analysis, we will ignore the weight of the beam itself and make a few assumptions. The first assumption is that the beam is sufficiently supported by upwards forces generated at points A and B. And the second assumption is that the support at A generates any horizontal forces that are required to keep the beam at equilibrium. The first step in constructing our FBD is to establish a suitable coordinate system. For this example, we will select up and right as our positive y and x directions and counterclockwise as our positive moment direction. The second step is to determine the part of the body that is to be studied and draw it out. In this example, we are interested in the entire length of the beam, so we will draw only the beam. Step 3 is to draw all the forces acting on the body. To do this, we have to replace the supports with their appropriate reactions. Remember that reactions are the forces exerted by supports to resist loads. The pin support at A is replaced by its horizontal reaction and vertical reaction, AX and AY. The roller support at B is replaced by BY since it only resists loads in the vertical direction. The fourth step is where we write and solve the corresponding equilibrium equations. First, we will solve for the sum of forces in the horizontal direction given Fx equals 0. Since the only force acting in the horizontal direction is Ax, we get Ax equals 0. For mathematical reasons, we calculate moments next. You may redo this example later to see why this is the case. For moments, we must indicate the turning point, so we will pick A as our turning point. The sum of moments about A equals 0, which is equal to By times its normal distance from A of 1.8 meters, minus the 6,000 Newton load times its normal distance from A of 0.6 meters. By is positive because it acts in the counterclockwise direction, and we're subtracting the 6,000 Newton load because it acts in the clockwise direction. Rearranging the equation, we can solve for By, which gives us a force of 2,000 newtons. Finally, we can solve for the sum of forces in the vertical direction, Fy equals 0. The forces acting in the vertical direction are Ay, By, and the 6,000 Newton load. Knowing that By equals 2,000 newtons from earlier, we can write 0 equals Ay plus 2,000 newtons minus 6,000 newtons. We then get a force of 4,000 newtons for Ay. The final step is to sketch and interpret the results. On this diagram, I am writing out all the forces that we just calculated. The reason as to why we solve for moments next is because in the equation of the forces in the vertical direction, we would have two unknowns, Ay and By. But we want to get rid of one of the unknowns, which was solvable by using the moments equation about A. We can also try taking moments about different points. Earlier, we solved this problem by taking the sum of moments about A, and the moment equation that we got was the sum of m about A equals 0, which equals By times 1.8 meters minus 6,000 newtons times 0.6 meters. Now pause here and try to solve the same problem, except this time take the moments about B instead. Taking the sum of moments about B, we get the sum of m about B equals 0, which equals negative Ay times its normal distance to B of 1.8 meters, plus 6,000 newtons times its normal distance to B of 1.2 meters. Ay is negative because it will act in the negative clockwise direction, and this time we are adding the 6,000 newtons because it will act in a positive counterclockwise direction. For the beam to be in equilibrium in the vertical direction, the sum of forces Ay plus By minus 6,000 newtons must equal 0. if we rearrange this equation for AY, we can then substitute 6,000 newtons minus BY back into the moment equation about B. After simplifying the moment equation, we will get 0 equals By times 1.8 meters minus 6,000 newtons times 0.6 meters. From the last slide, we got the moment equations about points A and B. Notice that these equations are the exact same, being 0 equals By times 1.8 meter minus 6,000 newtons times 0.6 meters. We can conclude that moments can be calculated about any single defined point, and it will still yield the same results. The last example we'll go over is on a roof support tower. A concrete pylon is built in at its base at A, and it provides an aerial anchor point at B for a roof support cable that carries a load of 50 kilonewtons. What are the reactions at A? Feel free to pause this video here to think of your answer. Following the steps from before, we will first establish a suitable coordinate system. Once again, I'll select up, right, and counterclockwise as our positive sign conventions. Next, we have to determine the body that needs to be studied. In this case, it is the tower, so I will redraw the tower. In step 3, we draw the forces acting on the body which occur at point A. Since the support at A is fixed, there will be a moment AM and reactions in the horizontal and vertical directions AX and AY. Now that we have drawn all our forces, we can move on to the next step where we write and solve the corresponding equilibrium equations. Before we solve these equations, it is important to note that the 50 kilonewton load is acting at an angle, and so we can break this force up into its corresponding X and Y components. Using trig, we get 50 kilonewtons times sine of 30 degrees for the X component and 50 kilonewtons times cosine of 30 degrees for the Y component. The sum of Fx equals 0 accounts for Ax and the X component of the 50 kilonewton force at B. Our equation will be 0 equals Ax plus 50 kilonewtons times sine of 30 degrees, which results in Ax being negative 25 kilonewtons. A negative value means that Ax will act towards the left. The sum of Fy equals 0 accounts for Ay and the Y component of the 50 kilonewton force at B. Our equation will then be 0 equals Ay minus 50 kilonewtons times cosine of 30 degrees. This gives us a force of 43.3 kilonewtons for Ay. Finally, the sum of moments about A is 0, which is equal to Am plus each of the component forces of the load times their normal distance to A. So Am minus 25 kilonewtons times its normal distance to A of 20 meters minus 43.3 kilonewtons times its normal distance to A of 25 meters. We subtract 25 kilonewtons because it will act in the negative clockwise direction, and same with the 43.3 kilonewtons because it will also act in the negative clockwise direction. Am will then equal 1,582.5 kilonewton meters. Notice that we have neglected the gravity loads on the tower. The last step is to sketch and interpret our results. In this diagram, I'm writing all of the forces that we just calculated. At first, we assumed that Ax was acting to the right, but since we got a negative value, we now know that it will in fact be acting to the left.